So, this equation of continuity can be understood and established with the help of a diagram where there is a tube whose area of cross section reduces to another tube, that is, suppose area is A1, it is A2. So, naturally for streamline flow the velocity at the wider part will be less than that in the narrow part. So, in a time delta t second, distance covered by the liquid is V1 delta t and here it is V2 delta t, but volume of liquid remains the same because it is streamline flow. So, main thing is for streamline flow volume of liquid flowing at any cross section is a constant. So, which means V1 is equal to V2 and it is a small cylinder. So, it is A1 then V1 delta t is equal to A2 V2 delta t. So, delta t cancels. So, you have A1 V1 is equal to A2 V2. So, this is called equation of continuity. This is called equation of continuity. It will be of use at many places, like say suppose you want to know Bernoulli's theorem. Here the axis is same for both the tubes, but let us think of a situation where the axis is not same, like So, this line represents level to measure potential energy. That means the height of the middle of the wider tube is H1 and here it is H2. So, here compared to the equation of continuity, there is a little difference. The difference is about the amount of potential energy. Kinetic energy is different. Here also velocity is less, here velocity is more. So, kinetic energy here this part is more. But here also kinetic energy, apart from kinetic energy, there is also potential energy. So, both are to be considered, along with another energy that is called pressure energy P1 and it is P2, because P1 greater than P2 ensures flow of liquid. Unless pressure is higher here, liquid will not flow. So, that gives rise to another type of energy called the pressure energy. So, that we will discuss. Pressure energy, potential energy and kinetic energy. So, Bernoulli's theorem is actually a principle of conservation of energy applied to this type of situation where the height of one tube is more than the height of the other tube. It may be less also, this side less, that side more, as given in the NCERT book. This side is less, that side is more. So, here this theorem is there is some restriction. This theorem is not always applicable. This theorem is applicable to liquids that are number one, incompressible. Number two is streamline flow. So, incompressible means the density of the liquid does not change. In usual liquids, we always find this situation, incompressible. I do not know whether compressible liquids are there. There may be some exceptions, but usual liquids, they are incompressible. That means density at this part is same as density at the other part. And for streamline flow, as you know, there is definition of streamline flow, and volume, mainly volume of liquid flowing at any cross section is a constant. So, here what we find, suppose pressure is P1. So, if P1 is equal to pressure at the wider end, comma, then P1 is equal to F1 by A1, force by area is your pressure. So, that implies force acting on the liquid, because the liquid has to be pushed through the pipe. So, there is some force applied to the liquid. So, work done on the liquid, at the wider end is equal to work done, as you know, that is force into displacement. So, it is F1, then displacement is V1 delta t. In a time delta t, the displacement is V1 delta t, and F1 is P1 A1 V1 delta t. So, that is equal to P1 capital V1. So, capital V1 is the volume of liquid flowing at the wider end. So, similarly, we can write work done by the liquid at the narrow end is equal to W2 is equal to F2, then V2 delta T, F2 is P2 A2, V2 delta T, that is P2 capital V2. Then one may think that how the liquid is able to do some work. Suppose there is a stone here. At the opening of the narrow end, there is a stone. So, when you push the liquid here, the liquid is able to displace the stone. That means the liquid is able to do some work. So, that work is W2, and it may be, it may not be. W1 is equal to W2. Usually, for this type of situations, W1 is more, and W2 is less. So, what is W1 minus W2? So, W1 minus W2, it is a work has the same unit as energy, and this type of energy is, as you see, that it is pressure energy, it is called pressure energy. So, W1 minus W2 is equal to change in pressure energy, is equal to P1 V1 minus P2 V2. Then question is, what happens to this energy? You have done some work at the wider end, and the liquid is able to do some work at the narrow end. So, the difference of these two energies is stored in the liquid in the form of potential and kinetic energy. So, change of potential and kinetic energy will give rise to the change in pressure energy. And how to know the change in energy? Change in energy you can know from final total energy minus initial total energy. So, this appears as change of potential and kinetic energies. So, to know this, the difference of the two energies. So, final potential energy plus kinetic energy minus initial potential energy plus kinetic energy. So, that will give rise to final potential energy. As you see from the diagram, it is mg h2 plus final kinetic energy is half m v2 square, where we have considered m gram or m kg of the liquid flowing. That means, mass of the liquid flowing is your m. So, mgh2 plus half mv2 square, then initial is mgh1 plus half m v1 square, and these two must be equal according to the principle of conservation of energy, because no energy can be destroyed or created. So, the difference of these two pressure energies is equal to the difference of the total of fine kinetic and potential energies. So, equating equations 1 and 2 gives P1 V1, then this part comes to this side plus mg h1 plus half m V1 square is equal to P2 V2 plus mg h2 plus half m V2 square. So, this is one expression for the Bernoulli's theorem. Then how to write this expression in language, which is called statement. Statement is, this is called first form of Bernoulli's theorem. You see, this is pressure energy, this is potential energy, this is kinetic energy. It is pressure energy, potential energy, kinetic energy. That means, the sum total of pressure energy, potential energy and kinetic energy is a constant. So, statement is for incompressible liquid and streamline flow, that is always there, sum of pressure energy comma potential energy and kinetic energy is a constant, where constant at any cross section of the tube. That is the first statement. Then we have noted that it is a streamline flow. So, for streamline flow there must be smooth flow. So, volume of liquid flowing at any cross section must be the same. So, we can find the other forms. There are another other two forms for the Bernoulli's theorem that we will derive. So, since the flow is streamlined, V1 is equal to V2 is equal to V say. So, in that case equation 3 will become P1V, then this thing, then P2V. So, dividing by V throughout, dividing equation 3 by V throughout, that means each term is to be divided. So, what you get P1, then M by V GH1 plus half M by V GH2 M by V, it is V1 square is equal to P2 plus M by V GH2 plus half M by V, then V2 square. Equation 3 is divided by V. So, that gives you P1 plus, what is M by V? Mass by volume is density. Density of the liquid, that is rho. So, V1 square, then that is equation number 4. So, what is this? This is second form. The second form of Bernoulli's theorem. So, what is the statement? For incompressible fluid, flowing as a streamline, the sum of pressure, potential energy per unit volume, because it is potential energy is mgh1 by V means per unit volume. So, potential energy per unit volume, then kinetic energy per unit volume is a constant at any cross section of the pipe. So, it is sum of pressure, comma, potential energy per unit volume and kinetic energy per unit volume is a constant. Is a constant at any cross section of the tube. Clear? So, this is another form. Then we will go to the third form. So, to get the third form from equation 4, let us divide by rho g. Let us divide equation 4 by rho g throughout. Each term is to be divided by rho g. Then what will happen? So, first term is P1 by rho g, second term is only H1, third term is V1 square by 2g. Then for the right hand side it is P2 by rho g, then plus H2 plus V2 square by 2g. So, it is equation number 5. So, this expression shows that there is a dimension. If it is checked, dimension is same for all, and it is height, so it is length, some length. This is also length, this is also length. So, this quantity, pressure divided by density and gravity, is called pressure head. This is elevation head. Height means elevation head, and this is velocity head. So, sum total of pressure head, elevation head and velocity head is a constant at any cross section of the pipe or tube. So, it is called pressure head. This is called elevation head, and this is called velocity head. So, this is the third form of Bernoulli's theorem. And naturally, the statement will be sum of these three. Statement will be sum of pressure head, comma, elevation head, and velocity head is a constant. At any cross section, of the tube. So, this is all about the Bernoulli's theorem, and this theorem has many applications. And we will go through some of the applications This was actually invented by Venturi. So, according to his name, it is Venturi meter, and the prime work of this device is to measure the volume of liquid flowing in a pipe. So, that one may think that if area of cross section is known, then velocity of flow if found out, then volume can be easily found out. But that is not so easy, because velocity of flow is to be measured particularly for a transparent liquid like water. It is difficult. So, water meters are based on this principle to measure the amount of water consumed by a person in his household. So, Venturi meter, it is a device to measure volume of water consumed. And water meters, just like electric meters, there are water meters to know this. So, water meters are based on this principle, this device. So, the So, this is like a U tube. So, here the axes of the wider and narrow tube are same. It is the axis, and it is say pressure is P1 at the wider end, and it is P2 at the narrow end. Naturally, P1 is greater than P2, and area of cross section is A1, and it is A2. So, here you see, compare the Bernoulli's theorem figure. Here there is H1 and H2, which are different. But suppose the level to measure potential energy is chosen on the axis. So, here level to measure potential energy is chosen as the axis. If the axis itself is the level to measure potential energy, then what happens to H1 and H2? They will be simply zeros. So, H1 is equal to H2 is equal to 0. Once we choose this type of level to measure the potential energy as the axis itself, so H1 is equal to H2 is equal to 0. Then from the third form, of Bernoulli's theorem, comma, we have it is P1 by rho g plus 0 plus half, then V1 square is equal to P2 by rho g plus 0 plus V2 square by 2g, because H1 and H2 are both zeros. Then if you equate them, g is in the denominator of both the sides. So that also cancels. So what you get? You get P1 minus P2 by rho. You bring this to this side and it is V2 square minus V1 square by 2g. Then we come to the use of the U tube. This is a U tube that connects this wider pipe and narrow pipe, and there you take an immiscible liquid. Suppose water is flowing here, you have to take mercury, because mercury and water do not mix with each other. So this is a immiscible liquid that does not combine with, say, suppose you take colored ink in this U tube, that will not do, because when water will flow, that colored ink also mixes with it and flows. So you cannot measure the pressure difference. So P1, P2, that is pressure difference, that is measured with the help of U tube. There is a height difference, as you see from the diagram. Pressure is more, so it is depressed more, and this is a H. Height difference is H. So it is HD G by rho is equal to, for V2 square you write A1 V1 by A2 minus V1 square by 2g. So where D is equal to density of the liquid in the U tube. In the U tube, and rho is equal to density of the liquid flowing. Density of the liquid flowing is rho, and here we have used the equation of continuity. A1 V1 is equal to A2 V2. So V2 is A1 V1 by A2. So this we have done to to have one variable. There are two variables V2 and V1. So to reduce that, we make it one variable, that is V1 only. Then what will happen? Then 2 HDG no, sorry, this G has already cancelled. So, therefore, no G here, only 2, because G taken common cancelled. But here it is HdG, height of a, that we will do in the next class, the pressure due to a liquid, that is HdG, that we will do. So, 2 HdG by rho is equal to, here you take common V1 square, then A1 square by A2 square minus 1, that is something as V1 square, then A1 square minus A2 square by A2 square. So, from this you find V1 square is how much? V1 square is 2 HdG, then A2 square divided by rho into A1 square minus A2 square. So, once you find V1 is how much? If you take square root, only A2 will come out, A2 comes out, and all other things are inside the square root. Then capital V1, small v1 is speed or velocity. So, capital V1 is the volume of liquid, flowing per second. Volume of liquid flowing per second, that is equal to A1 V1. So, this will come out to be A1 A2, then square root of So, this is the final result by which one can find the volume of liquid flowing per second, and the time, suppose it is given for 1 hour it is used. So, you multiply with time to get the total amount of liquid flowing. So, this is the first application, and another application is your atomizer. So, what is the atomizer? One may think that atomizer means to produce atoms. That is not the case. That means to produce very small particles, like a spray. Suppose there is a spray. So, there you use very small particles. So, very small particles are prepared with the help of this device, that is atomizer. So, it is a rubber bulb, or you can say bulb also, because the structure may not be spherical, it may be slightly different. it is called nozzle. Nozzle means there are many small holes here. So the liquid will go like this through this. So it is the bottle containing the liquid to be sprayed. So here the bottle should not be completely full. That is one restriction, because by that some air has to be inside. If some air is inside the bottle, then the pressure on the liquid, downward pressure, is the atmospheric pressure. So P0 is equal to atmospheric pressure. P0 is the atmospheric pressure. So what it contains a rubber ball attached with a horizontal tube, and there is a vertical tube also starting from the horizontal tube, and it is inside the bottle. So at the first instant, suppose you squeeze it, suppose you squeeze it, then the volume of the ball decreases and some amount of air goes out with some velocity. And from Bernoulli's equation, that is third form equation, you can easily see that when velocity increases, at that time pressure decreases, because there is sum total of pressure, then sum total of pressure, then elevation is 0, suppose axis is same, so elevation is 0. So pressure plus velocity on one side is equal to pressure and velocity square on the other side. So once this velocity of the air increases in the horizontal tube, pressure decreases. So therefore here inside the tube pressure is P, and this P is less than P0. Once this pressure is less than P0, the liquid rises. The liquid rises up to the horizontal tube, and when liquid rises and you continue squeezing, then this amount of air moves along with the liquid through the nozzle in the form of small droplets, which are used in the sprays, any type of spray, say for medicine work there is spray, then for also beautification work there is spray, like that. So this is the basic principle, that is and this is not a continuous process. Once you squeeze it completely, you have to allow for the original condition to be restored, because after allowing it to open, again air comes and the process can be started again. So, by squeezing some air goes out through the horizontal tube, and pressure decreases. The liquid rises. Just like we take the say cold drink. When you take cold drink, you take air so that the pressure decreases and the cold drink enters into the mouth. So, the liquid rises, then further squeezing results in the forceful expulsion of air and liquid through the nozzle as very small particles, and that is why the name is atomizer. They are not actually atoms, but very small particles. So, this is one application. Then the third is blowing of the roof of houses during cyclone. You see, suppose we think of a house, not concrete roof house, but a tin roof or say asbestos roof, that type of thing. This is door and there is a window also, and common sense or what we do in general is, if cyclone comes, before cyclone comes, we close the doors and windows. If you close the doors and windows, the air inside the room is the atmospheric pressure, and this atmospheric pressure is P0, this side, that side, because pressure is exerted on all sides by equal amount. So, this is atmospheric pressure, P0 is the atmospheric pressure, and then when actual cyclone arrives with a high speed, so V is equal to high. Velocity is high, so when velocity is high, the pressure is less. So, when pressure is less, P is less than P0, and this is due to Bernoulli's theorem, because velocity high means pressure term plus velocity square term together is a constant. So, when velocity is high, pressure is less. So, pressure P is less than P0. Then, if the roof of the house is light, not very heavy. If it is concrete, it is heavy, otherwise it is quite light, halka. Then this pressure inside the room pushes the roof to some amount. When it pushes through some amount, the cyclone takes the roof away. Walls are unaffected. So, in villages sometimes this happens. So, they bring the roof back. Suppose it is tin, then they bring the tin back and again fit it. So, that is possible. So, here when doors and windows are closed during cyclone, the pressure inside the room is the atmospheric pressure. Is the atmospheric pressure P0. So, when velocity becomes high, pressure decreases. So, P0 minus P, this is the pressure difference. This applied on the roof. The roof has some area. So, when pressure difference is applied on the roof, there is force. So, P0 minus P applied on the roof causes the roof to be raised and blown away. By the wind. So, roofs are destroyed, but the walls remain intact. Then another application is the spinning of a cricket ball. Suppose there is a cricket ball and it is thrown into air, making a clockwise rotation. The thrower is capable of producing spin. So, this is the ball. Then in the air there is some wind. So, wind. So, wind velocity is omega, say. Wind velocity is omega. This wind velocity should not be high, because if it is very high, then cricket game cannot be played. So, the wind is there, but it is not very high. So, if it is clockwise rotation, then at this point the speed of the ball is v. So, v is this side, wind is this side, so it is V minus omega. And here on the top it is V plus omega. Wind is same thing as direction of the velocity of the ball. So it is V plus omega, it is V minus omega. Then what happens? The ball experiences two types of velocities. One is higher, the other is lower. So the stability of the ball is in question. That means the stability is not there, so it will go in arbitrary directions. So that is the cause of uncertainty in the movement of the spin ball. So two velocities on the ball produces arbitrary movement. And the motion becomes unpredictable. Motion becomes unpredictable.